So in this problem, they have a student conducted an experiment, and it says determine the molar concentration of solutes in chicken eggs. And they say that the eggs were soaked in white vinegar to remove all the shells. And then they say eggs were placed in sucrose solution at different concentrations. All right. And they give you the data here. They say the sucrose concentration in moles per liter is here. The initial mass is grams is here. The final mass is here. They even do the subtraction for you and give you the change in mass. Then they have the percent change in mass, and they write the percents here. So this is the change in mass, so it's going to be negative and positive. They're using the most appropriate data, construct a labeled graph on the axes provided, and I gave you graph paper, and you had to create your own axes. So an axis generally runs like so. Now, normally we will want to pick this point here at, if I look here at that point, that is usually your 0, all right, usually, on both x and y, all right? And so what you start with is when you're looking at molar concentration. So what I love to do is draw it out. I have a solution. I have an egg without a shell. Let me just... an egg without a shell, and it's sitting there in a solution, and the solution is of different molar concentrations. So you have that solution can be anywhere from 0 to 0.5 moles per liter. Back from when you were in chemistry, 1 or 2. Those are your options. So this is, you control that. You control the moles per liter, the molarity of the solution, moles per liter. Molarity of the solution, you're controlling that. It's either going to be 0.5, it's going to be 1, or it's going to be 2 or 0, right? 0, 1, 2, 0.5. And because you're controlling it, we call that the independent. So you're expected to know that your independent data, I'm just going to put an I here. Your independent data, it's expected that you know that your independent data goes on the x-axis, and that your dependent data goes on the y-axis. Now, what depends on the concentration of the solvent? Concentration of the solute, rather. In this case, the solute is sucrose, which is a disaccharide. So it's not going to pass through the membrane easily on its own. So that means water's going to move. So what's going to change is whether water goes into the cell or does it go more out of the cell. In which direction will water move more, in or out of the cell? That's the only thing that's going to change depending on this concentration difference. So when you're dealing with sucrose, whether it's going in or out of the cell depends on this. whether water's going in or out of the cell depends on this. So what goes on the independent x-axis? The thing that goes there is the sucrose concentration. In molar sucrose concentration. You don't have to write independent here. I'm just writing it as a moment, using this as an opportunity to discuss this. So I'm going to erase that. So there should be no doubt. The axes should be labeled sucrose concentration. So what am I graphing if I want to know the difference in percent mass change of the egg in the different sucrose solutions? Well, I should be putting the difference in percent mass change as the dependent. So how do I know what that is? My goodness, it's labeled right here. It says percent change in mass. So when I read this percent mass change, it says it right here. So I'm graphing this versus that. So what would the title of my graph be? Title of my graph would be sucrose concentration, and I could put it in square brackets to save myself some time, in molar versus percent change, triangle, in mass. Triangle means change. It's just a quick way of me writing it, but you could write it out in words. It could be anything like that. So that would be the title of my graph. And of course, on the y-axis, what I'm going to write is percent mass change, percent change in mass, percent change in mass. It's percent, so it's not grams or what have you. Some of you grabbed the mass, some of you grabbed the final mass, the initial mass. What they asked for, read the question, is the difference in percent mass. They said it right there. And that's percent change in mass. So, percent mass change. So you're graphing two things. You're graphing this column versus this column. So, all right. So then we know we're percent mass change. The numbers are there. So now I just have to find the scale. Well, the sucrose concentration, that one should be pretty easy. It goes from 0 to 2. So I go from 0, which is already here. I know all the far right, I have to have 2. I gave you graph paper so you can count the number of divisions, which are the lines, the vertical lines. In the middle, I'm going to put 1. So I know that my 0.5 is going to be here somewhere. My 0 is going to be here, my 1 is here, and my 2 is there. Done. Then the next goes anywhere from negative 13 to 4. So now, don't know how you want to do this, but I can't tell you how many people put negatives. Let's go over number lines really quickly. If I have a vertical number line, my 0 is here. I have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 goes up the positive side, and then down is negative. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, and negative 10. Negatives are here, positives are here. Above the 0, below the 0. It's number lines, right? Okay. So some people mixed it all up. I'm assuming what was going on is that people were placing the numbers here in order of how they were placed here, is my guess. I'm going to warn you, I'm going to remind you of your algebra days and say, look, you got this graph. You can think of a graph this way, where this side, in this quadrant, it's a positive x and a x and a negative y, right? This whole area here is going to be a positive, all your positive x's and your negative y's. Up here, you're going to have your positive x's and positive y's, because all these y's are positive, all these x's are positive, so this is your positive x and positive y's. Over here, you're going to have positive x and negative y. And down here, you have negative x and negative y. Like, that's what you should be thinking of when you're thinking of graphing. You should be thinking of, well, gee, over here, if I have a negative x and a negative y, I have to be in this quadrant. If I have a positive x and a negative y, it's going to be in this quadrant. And if I have a positive x and a positive y, it's going to be in this quadrant. So when we look at here, these are all positive, 0 to positive. So for sure, my x's are going to be somewhere, all my points are going to be somewhere here in this area. So I'm not going to have anything to the left of there. Then here, my y's, remember I said I know this is y because that is what's changing because of the concentration of the solute. So this starts at negative 13, goes all the way to 4, let's say 5, a little bit more than 4. So rather than changing my 0, I'm just going to draw a line downward. And I'm going to say, I'm going to start it here at negative 13. So I think it's a little more than negative 13. I think it's negative 13.5. So I'm going to start at negative 14. So here we have negative 14, and the highest number is 4. So I'm going to take this, but if I go 1, 2, 3, 4, right? 5, 6, 7, 8, 9. I could do that here to 14. So you can do anything like that, negative 14 to 14, or you can just focus on looking at the graph and just focus, stopping here at 4, however you want to handle it. But you have to number these 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you have to number them pretty evenly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After 4, it doesn't matter because my positives, if you look here, my biggest positive number is 5. Hello, we have a class change, so we have to deal with the noise. 3, 4, 5. So my biggest class change, biggest number is 5. Lowest one's negative 14. So now I just had to plot my points. My 0 had at 4.11. My 0 was at 4.11. I'll put my dots here. 4.11, so something like here. My 0.5 was at 2.04. My 0.5 was 2.04, so it's around here somewhere. And my 1 was 7.12. My 1 was negative 7.12, so 1, 2, 3, 4, 5, 6, 7. 0.12 is around here somewhere, so I'm going to 1. So again, 1, 2, 3, 4, 5, 6, 7.1. So my 1 is going to be somewhere around here. Of course, I'm not using graph paper, so it won't be perfect. And then my 2 is negative 13.44. So it's somewhere around here. So if I drew a best fit line through this, it would look something like that, right? So my percent change, as the concentration of sucrose went up, I lost more and more water. So more water went out. So I had 2 situations. In the negative, it was when I was losing water, I had my egg. So I had an egg. That egg was losing water. It was shrinking because, why was it shrinking? Because my concentration was higher than the isotonic. So my concentration of solute was higher, so water was leaving. Let me use blue. My concentration of water was higher going out than it was going in, so the egg shrank. Water was leaving. Where had I drawn the same thing with the positive y values, the percent change was a positive percent change. Why did it change positively? Because water was going into the cell. Water was going into the cell. So because water was going in, yes, you had some water going out, of course. You had some going out. But the opposite was going on in both directions. But there was more water going out than in the bottom, and more water going in than out at the top. So this was in a hypertonic solution. So when you went to go explain it, the explanation is that when it was in a hypertonic solution, the percent change was negative. When it was in a hypotonic solution, the percent change was positive. And then here, when there was no change, right, at 0, there was no change, that's where it was isotonic. So if they didn't ask you this, but if you wanted to identify the isotonic, this point right here is isotonic, where there was no change in concentration. So that's the concentration, right? Whatever concentration that is the concentration of the solution. Now you might ask, well, why is there a dot up here? Because this is the best fit line. And so we're expecting there to be some error. So you'll note that none of the points are on a line except maybe the first one. All the rest of these, right? All the rest of these are off the line. But here would be the isotonic solution where the percent change is 0. So that's how you read this graph. That's how you answer this question. Going back to number line and quadrants and just making sure you're reading the question and putting in the right answer. That's it.